let's talk about some properties of the SVD. Again, we said this before, but the rank of A is equal to the number of non-zero singular values. That's pretty sweet. Given the SVD, we can give you the rank of the matrix, no worries. In terms of norms, we'll talk about norms in a different video, but the matrix norm, the induced matrix norm and the 2 norm is equal to the highest singular value. The Frobenius norm of the matrix is just the square root of the squared sums of each of the singular values. We're going to go up again to R only because everything after R is 0. It won't have any effect. The determinant of A can be determined, pun intended, just by taking the product of all of these singular values. So that's, sigma 1, sigma 2, sigma R. Well, actually, this is sigma n, because if the rank is less than n, then the matrix is singular and our determinant is 0. This makes sense, actually. So we do go all the way to n. You can get information about the range of A is just going to be the column space U1 up to UR. The null space of A is equal to everything after the R term in V. My favorite thing about the SVD, why it's my favorite thing in linear algebra, everything's like, oh, if the matrix is this, if the matrix is non-singular, if it's SPD, if it's symmetric, if it's square, blah, blah. The SVD does not care, doesn't care. Every single matrix, every matrix A has an SVD. I'm going to put 3 exclamation marks. That's how cool that is to me. One more last point, singular values are uniquely determined. Remember, we said that they all have to be greater than or equal to 0. Can we play with some minus values in the U or V's? Sure, but the singular values themselves are uniquely determined.